everybody, and welcome to our last video in thermodynamics, which we're going to cover a couple of different things here. But all of this stuff I feel that you'll find relatively easy. So we're cruising. We're doing really, really well. So we've talked about, heat of reaction, and we've talked about, heat of solution and heat in general and calorimetry and all of that. We're going to kind of bring this back a little bit because I think that actually this video might be one of the easiest of all of them because we're kind of putting together things we've already done. And let's talk about what the standard enthalpy of formation means. So if you think of forming something, right, we're forming something new from what was previously there. And in this case, we're going to be forming generally new compounds from its elements for the most part. Okay, so how much energy is required to form a compound from its elements? And if I look for water in this particular reaction, looks like hydrogen gas reacts with oxygen gas, and that forms two water molecules. And for this process to occur, my enthalpy of formation, so in order to form water, the heat that's involved in this reaction, we would release 394 kilojoules of energy. And we call that the standard enthalpy of formation. So the change, of course, is the change in the enthalpy. The H is enthalpy. This F stands for formation. So it's just the formation of the compound from its elements. And this little knot, I kind of wrote over it, but we'll see it there. That knot symbol means that this reaction is occurring at standard thermodynamic conditions, not at STP, at standard thermodynamic conditions. And the standard thermodynamic conditions is 298 Kelvin, which we know is 25 degrees Celsius, and it's 1 atmosphere. So not quite STP. If you think back to gas laws, STP is 1 atmosphere. So the pressure is the same, but the temperature is a little different. Standard temperature for gases is 0 degrees Celsius or 273 Kelvin. For more thermodynamic applications, we use 25 degrees Celsius. So additionally, the F subscript, we said, stands for the formation, meaning that the product of this reaction is being formed from its elements, which we said right here, okay? So let's get a definition for this, which actually we've already kind of talked about, but we'll get a nice little formal definition here. The standard enthalpy of formation is the heat that's associated with the formation of a compound from elements in their standard state. So the standard state, again, just means 1 atmosphere and 25 degrees Celsius. And here's something to consider. So the lower the delta, the heat of formation, the enthalpy of formation, the lower the delta HF, the more stable the compound is. So for example, in the process of producing water, this is a very low heat of formation. It's way below 0, okay? So this water molecule is very stable. Water likes to exist because it releases a lot of energy in that process. So the more energy that a product releases when it's formed, or a compound releases when it's formed, the more stable it is. Endothermic reactions typically don't want to occur because they need to absorb heat from the surroundings. It's much easier for reactions to release heat in the process. So the lower the heat of formation, the more stable the compound is. And actually in class, we're going to look at this because I have a chart that has a whole bunch of standard enthalpies of formation on it. So we could see really how stable some of these compounds and elements are. And we're not going to work with that too much otherwise, but we can use the standard enthalpies of formation to determine the enthalpy of a reaction. And we could do that by using Hess's law, which we've already used Hess's law already. And you guys were very good at that from what I remember. So we can use Hess's law to figure out, okay, well, what is the standard enthalpy of these reactions? So, unfortunately, hopefully I gave you this paper already so you could use this, but otherwise you might not have it yet, so I'll just have to tell you what these enthalpies of formations are. So let's do sample problem 12. Using the standard enthalpies of formation and Hess's law, determine the enthalpy of the following reaction. So we want to know what's delta H for this reaction right here. And what we can do is by looking at a chart that lists the standard enthalpies of formation, you can determine what is the delta H of formation for this, what's the delta H of formation of that, and that, and that. And we can manipulate those equations using Hess's law to get this total reaction. I'm going to stop talking about it and let's just do it. On a chart that lists the enthalpies of formation, we're going to look up CH4. And this process looks like so. So 1 carbon plus 2 hydrogen molecules produces CH4. So this is the enthalpy, this is the reaction to form methane from its elements. So 1 carbon plus 2 hydrogen molecules give me this. And the delta H of formation for that process is negative 74.87 kilojoules. Next one right here. So this is an element, okay? Elements will have an enthalpy of formation of 0 right here. So actually, we're not going to include this in our reaction because we're going to see it kind of comes into play. We have to get some chlorines from this guy and we have to get some chlorines from this guy. So we're not going to worry about this element. So elements always have a delta H of formation of 0. So you don't have to worry about those. Let's look up carbon tetrachloride. So 1 carbon plus 2 diatomic chlorines gives me CCl4. And the delta H for that process is negative 135.4 kilojoules. And I'll look up this last guy here. So this one's a little interesting. Now, normally you'll be given these equations, so I'm sorry that you might not have them already. But here's this next reaction. So 1/2 hydrogen plus 1/2 chlorine gives me a hydrochloric acid. And the delta H of formation is going to be negative 92.31 kilojoules. This should all have a little knot there. We can use Hess's law like we've already done to figure out what's the enthalpy of that reaction that's represented. So let's go ahead and manipulate this. I don't know if I'm going to have enough room on this pad. You might have enough room on your paper, but let's go ahead and start changing a couple things. Looks like my methane's got to be on the reactant side. So I'm going to flip that. CH4 makes, oops, that should be an arrow. Carbon and 2 hydrogens. What does that do to my delta H? Makes it positive. 87. Looks like carbon tetrachloride's on the right side, so I'm going to leave that guy. C plus 2Cl2 gives me CCl4. Delta H stays the same. Negative 135.4 kilojoules. And then it looks like I have this one, and this guy's on the right side as well. So, except I do need 4 hydrochloric acid molecules. So I'm going to multiply this guy by 4. So 4 times 1/2 is 2 H2s. 4 times 1/2 is 2 Cl2s. And 4 times 1, of course, is 4 HCl. Oh my God, I keep screwing up here. And this is why I like to teach Hess's law first, because you can use Hess's law for a lot of stuff. And if I take negative 92.31 times 4, I get negative 369.24. Let's add all these up. So if I add these guys up, I get negative 429.8 kilojoules. But let's make sure that these guys all cancel out. So looks like I have a carbon on both sides, reactant and product, so they cancel out. Looks like I have my two H2s. They also cancel out. Otherwise, it looks like everything's pretty good. So I have a CH4 and 4 chlorines, because I have them on both sides. 4 Cl2s gives me CCl4 plus 4 HCl. And that reaction matches this guy right here. So here is how we can use those enthalpies of formation to figure out what's the enthalpy of a reaction. Okay, that all works out. Hess's law again. So not anything new that we're doing there. Another way that we can determine the enthalpy of a reaction is by using this equation. And I believe College Board likes this equation a lot more than the last one. I'm sure you will too, because it's actually quite easy to use. So the delta H of a reaction, the heat of a reaction, is equal to the sum of the heat of all the products minus the sum of all the heat of the reactant. So remember, this right here is the sum. We got to add them all up. So we're going to do the same exact thing, except we're going to calculate. Hopefully we get this number again, but we're just going to use these delta H's up here for each of them. So I'm just going to identify which is which. So the heat of formation of methane is negative 74.87. This guy's 0. Carbon tetrachloride is negative 135.4. And hydrochloric is negative 92.31. Those, again, like I said, you could find on the standard enthalpies chart. Let's go ahead and solve for this. So my heat of the whole entire reaction, that's equal to the sum of the products. So I have CCl4. I have negative 135.4 kilojoules per mole, technically. And there's 1 mole of that because there's only a coefficient of 1. So I'm going to times that by 1. And I'm going to add that to the hydrochloric. So this is negative 92.31 kilojoules per mole. But according to this balanced chemical equation, there are 4 moles of hydrochloric. So I'm going to times that by 4. This is the sum of my products. So I have 1 carbon tetrachloride and I have 4 hydrochlorics. I'm going to add all of that up and get some number. And actually, I could do this for you now. When I add all of these up, we get negative 504.64. And units are kilojoules, because if I'm multiplying this by 1 mole and this is 4 moles, moles and moles will cancel. So I'm left with, oh, I'm sorry, this should be just joules. Nope, no, it is kilojoules. I'm sorry. Kilojoules right there. Let's finish my reactant side. So looks like methane, I have negative 74.87 kilojoules per mole. Oops. And there's 1 of them. So I'm going to times that by 1. And I'm going to add that to, but chlorine's got a 0 value for enthalpy of formation. So that's 0 kilojoules per mole. And I'm going to times that by 4. When you solve this part of the reaction, I have negative 504.64 minus negative 74.87 kilojoules. So when you do that final part, so negative 504 plus technically 74.87, I get a delta H of reaction that's equal to negative 429.8 kilojoules. Check that out. This guy and this guy match each other. Like I said, College Board much prefers the second one because they will always give you the heats of formation. So they'll just give you a list and you'll have to solve for it that way. It's actually quite simple. So We'll do a bunch of these in class, but I don't think you'll have any trouble with these at all, as long as you know it's the sum of the products minus the sum of the reactants. Let's try one more in this case. So let's calculate the enthalpy of vaporization. We could also do this not just for reactions, but also through phase changes, because that standard enthalpies of formation chart should have a lot of substances in different phases. So it looks like for carbon disulfide liquid, the value for this is 89.70 kilojoules per mole. And carbon disulfide gas is 116.9 kilojoules per mole. So in order to find the enthalpy of vaporization, again, it's not a heat of reaction because it's not reacting, it's just vaporizing. So it's still the same process, but just be cognizant of whether it's a reaction or a phase change. So in this case, it's a phase change. Same exact process. The enthalpy of vaporization is equal to, I really only have one reactant here, so it's actually quite simple. 116.9 kilojoules, and there's 1 mole, so the moles cancel, minus this guy, 89.70 kilojoules. And your answer is 27.2 kilojoules. Now this makes sense because in order for me to go from a liquid to a gas, I have to input energy. So of course my enthalpy of vaporization will be positive in this process because energy must be added in order to go through this phase change. So makes a lot of sense. This reaction, the one that was up above, actually a very favorable reaction because we are producing a heck of a lot of heat in this process. The heat is a very exothermic process, so works out great. Here's another example. We can also figure out the enthalpy or heat of reaction by looking at individual bonds. So not only can we determine the heat of reaction using the enthalpies of formation, we could do it again by looking at how much energy is involved when I break bonds or if I reform new bonds. So let's look at bond energy here. So during a chemical reaction, bonds are broken and new bonds are formed. These events change the potential energy of a system and can be used to calculate the approximate enthalpy of reaction. So these are not as good of an indicator, but they're still relatively close, okay? So let's consider that production of water again. So I have this reaction here. We found that the heat of formation of hydrogen is 0, heat of formation of oxygen is 0, and your heat of formation of water is negative 242. And you might see that's a little bit off, and that's because this is the amount of energy per 1 mole of water when it's being formed. So just keep that in mind as to why those two values are a little bit different. And you can calculate the heat of reaction. So if I take the sum of those products minus the sum of the reactants, I get negative 484 kilojoules per mole. Let's go ahead and consider, okay, well, what about the energy of the bonds and how does that affect your heat of reaction? So here I have to break 2 hydrogen-hydrogen bonds, okay? And I also have to break 1 double bonded to oxygen. So oxygen bonded to itself. In order to break bonds, breaking bonds requires energy. Right here. So in order to break those 2 single bonds and to break that double bond, I got to put energy in. However, when I reform the new bonds or when I form new bonds, so in this case, I'm forming 4 oxygen hydrogen single bonds. I have 1, 2, 3, 4 bonds. Those bonds are going to release energy. So depending on how much energy is required to break the bonds, and comparing that to how much energy is released when those new bonds form, that's going to tell us the heat of the reaction. So on this next paper, I have a list of some different bond energies, and all of these are in kilojoules per 1 mole. So here you'll see, these are all single bonds in this top section. A hydrogen bonded to another hydrogen, a single bond, has a bond energy of 432 kilojoules per mole. If I have a hydrogen atom bonded to an iodine atom, that is going to be a bond energy of 295. In this bottom section, right here, you'll see some multiple bonds that are listed. So let's use that to do some examples here. So using bond energies, calculate delta H for the reaction, just like what we did before. Reaction's a little bit different here because normally we always do products minus reactants. In this case, it's different. It's the sum of the energy of the bonds that are broken minus the sum of the energy of the bonds that are formed. There's an acronym that's used to remember this. It's basketball. Basketball is my best friend. Bonds broken minus bonds formed is going to give you the heat of the reaction there. So this is the only one where it's reactants minus products. Let's take a look. If I look at this chart above, in order for that reaction to occur, we said already I have to break 2 single bonds to hydrogen, okay? So hydrogen-hydrogen single bonds, we have already said, has a bond energy of 432. So bond energy here is 432 kilojoules per mole, but there are 2 of those bonds, so I'm going to times that guy by 2. I also have in my reactants a double bond to oxygen. So oxygen double bonded to another oxygen. And I look here, there's the energy of that bond. So that's 494 kilojoules per mole. But there's only 1 of those right there. So we look here, in order for this reaction to occur, 2 molecules of H2 reacts with 1 molecule of O2 to give me 2 molecules of H2O, but in my products, I have 4 oxygen-hydrogen single bonds. So here, I have an OH bond. That has a bond energy, if I look above, oxygen bonded to hydrogen is 459 kilojoules. And I got to times that by 4 because there are 4 of those bonds. So if I multiply all these numbers, 432 times 2 gives me 864, kilojoules. This guy just gives me 495 or 494 kilojoules. And 459 times 4 is going to give me 1836 kilojoules. Now, these bonds right here are the bonds that are broken. And then these bonds down here are the ones that are formed. So I have to take the sum of the bonds that are broken. So my 864 kilojoules plus my 494 kilojoules. And I'm going to subtract from that the bonds that are formed, which is 1836 kilojoules. And when I do that, I get negative 478 kilojoules. This is the heat of reaction looking at individual bond energies. And if I look at the previous page, we already said that to break this using the heats of formation, we get negative 484 kilojoules per mole. That's pretty darn close to negative 478, right? So not too bad. Although I believe the heats of formation is a little bit more accurate. We can also use bond energies for these too. And remember, the more negative the value for delta H is, the more exothermic the reaction is. Let's do 2 more together right here. So calculate delta H for this reaction right here. Compare your answer to the standard enthalpy of formation. We could draw this out if we want to, but I think this one's pretty easy. I have 1 molecule of H2. I have 1 molecule of F2. And I have 2 molecules of HF. So it looks like I have to break 1 H molecule, 1 hydrogen-hydrogen bond, one fluorine-fluorine bond, but I have to form two hydrogen-fluorine bonds. So let's set up something like this. Let's do bonds broken minus bonds formed. So in this case, my bonds that are broken, I have an HH bond. These bonds are 432 kilojoules per mole. And there's one of them. I'm going to add that to my fluorine. So the bond energy of a fluorine-fluorine bond is 154 kilojoules per mole. And again, I'm going to times that by 1 because there's only one of them. And I'm going to subtract from that the sum of the bond energies for the HF molecules. And if I look, these hydrogen-fluorine single bonds have a bond energy of 565 kilojoules per mole. But there are two of them. And if we solve for that correctly, we get negative 544 kilojoules. So in order to form hydrofluoric acid, gaseous hydrofluoric acid, we would release 544 kilojoules of energy based on bond energies. But it's asking us to compare this to the enthalpy of formation. And if we look at the enthalpy of formation is negative 545 kilojoules. That's pretty darn close. So in this case, we're at a pretty good approximation using bond energies. Remember, College Board loves to use the heat of formations more than bond energies, but you will have to know how to do bond energies as well. And remember, it's always reactants minus products. That's one reason that students can sometimes get confused. So for sample problem 17, we actually don't have to worry about some of these bonds because we'll notice that some bonds actually aren't broken in this case. And we can tell because I have a carbon-hydrogen single bond here, and I also have that same carbon-hydrogen single bonds there. So we don't have to worry about those when we're calculating our bond energies. And I also have a second guy, this one and this one. We don't have to worry about those two bonds when we are doing our calculations because they're going to cancel out in the end anyway. So if you can recognize that, that's going to make your life a little bit easier. That's a little less work you have to do. Let's look up some bond energies here. So let's look at these bonds that are broken first. I have a triple bonded carbon bond, and that has a bond energy of 839 kilojoules per mole. Notice how this is a much higher value. That makes sense. Triple bonds are much stronger than your double and single bonds. I also have two H2 molecules. So I also have to break two hydrogen single bonds. So H times H, or H bonded to H, gives me 432 kilojoules per mole. But I got to times that by 2, times that guy by 1. So this is 839 kilojoules. And 432 times 2 is 864 kilojoules. These are the bonds that are broken. Let's take a look at bonds that are formed. Looks like I'm forming a carbon-carbon single bond in this case. So my carbon-carbon single bond has a bond energy of 347 kilojoules per mole. And there's one of them. So that's 347 kilojoules. I'm also forming 1, 2, 3, 4 carbon-hydrogen single bonds. And those have bond energies of 413 kilojoules per mole. But in this case, I'm forming 4 of them. So 413 times 4 is 1652 kilojoules. These are the bonds that are formed. In order to calculate what's the heat of reaction, so my heat of reaction is equal to the bonds that are broken. So if I add these together, 839 plus 864 gives me 1703 kilojoules minus the bonds that are formed. So 347 plus 1652 gives me 1999 kilojoules. And we'll see this would be an exothermic reaction. Let's calculate 1703 minus 1999 gives me a value of negative 296 kilojoules of energy that's released in this reaction. This is an example of an exothermic reaction. That's it for thermo, right? I really truly feel like this will be very simple for you since we just got out of acids and bases, right? Anything is easy after that. So we're not going to take that much time with this. We're kind of on a little bit of a time crunch here, but we'll practice it a little bit in class. But otherwise, we're going to move on to applications of thermodynamic next. And that's where it starts to get a little bit more exciting. So I will see you in that video, and I will talk to you later. Bye.